Yeah, so I'll be speaking about how machines are transforming the way we do mathematics. So, this is a time of great change, I think, well, in general, for everything really, but also mathematics. Mathematics, we're a very traditionalist discipline. I think, like we still use blackboards. I have 4 blackboards in my own office. Other sciences, where they've embraced sort of big science, where they have 50, 500, 5,000 collaborators. I think mathematicians have somewhat reluctantly moved from like 1 to 3, yes, or 5 in collaborations. So we still do things in many ways like we've done for centuries. Working on individual problems, advising individual students, but it's changing. So we are using machines now, in particular, in many interesting ways. Not yet at the point where there's sort of a revolution. There's not yet a killer app. It's kind of like if the internet had been invented, but not yet email. Email was the first killer app for the internet that really triggered mass adoption. And we're not quite there yet, but you can sort of see it coming. Right, so I'll be talking about how machines have been influencing mathematics. I know many of you are not mathematicians. I'll be talking about some examples of research mathematics, but at a very high level, there'll be no actual equations or anything. For instance, well, actually, no, you'll see some, but not. That won't be the main focus. It's the kind of artistic background in some sense. So, in some sense, we've been using machines longer than anyone else. Okay, so we've been using machines to assist mathematics for millennia. Here is a machine assisting a mathematician from the first century. But what's different is the scale of just how much machines can help us, but also the nature, how machines are helping us. Right. So what have we been using machines for? So historically, for centuries, okay, so the abacus is already an example of computation, but besides computation, just building tables. In the early Middle Ages, people started building trigonometric tables and logarithm tables, and this just made certain computations much easier to do. And of course, these tables are completely obsolete now because we have calculators and then computers and so forth. But we still we still rely very much on lots of tables. We just call them databases now. But there has long been a tradition of experimental mathematics. It's very much smaller and honestly not as well respected as it should be compared to theoretical mathematics, which is like 99% of mathematics. So it's very imbalanced. I do feel like in the future we're going to have a much more balance between theory and experiment, closer to how it is in the other sciences. But it has a history. So, for example, in the 18th century, Legendre and Gauss famously investigated prime numbers so Gauss in particular, who was himself a kind of human computer in many ways, that built tables of like the first 100,000 prime numbers, and they conjectured the prime number theorem, which was then proven a couple of centuries later. But the experiments came first. And in a very similar vein, one of the major open questions in number theory nowadays, something called the Birchon-Swinton-Dyer conjecture. It's a conjecture about elliptic curves, and I'm not going to talk about what it is. But again, it was first discovered by compiling lots and lots of tables of elliptic curves, computing various statistics of interest, and noticing experimentally a very strong relationship between two otherwise unrelated objects. We still don't know why they're related, but we strongly believe they are. And this led to this conjecture. Perhaps the biggest and most successful mathematical database is called the Online Encyclopedia of Integer Sequences. This is something that many mathematicians use in some fields almost on a daily basis. The thing is that the literature on mathematics is huge, and if you discover that you're working with a mathematical object, if you're lucky, you know the name of it and you can look it up on Wikipedia, or maybe you know an expert in the right area and you can ask them, what's known about this object and so forth. But often there are two mathematicians across the world who have worked on the same object, but they don't realize it because they call it different names. They have no way of comparing or searching even. Has anyone else dealt with this funny thing? But many objects in the world, in mathematics, come with integer sequences. So like if you're studying, I don't know, Platonic solids, for example, there are 5 Platonic solids, and there's a tetrahedron with 4 vertices, there's a cube with 8 vertices, and so forth. And so there's a certain sequence of numbers that you can attach to many mathematical objects. And Niels Sloan had this genius idea that, well, why don't we just actually make a database of all the integer sequences that have ever come up in a mathematical problem somewhere, or at least as complete a database as you can hope for. And so this has now become the online encyclopedia of integer sequences, hundreds and thousands of sequences. And every day, a mathematician who's trying to understand an object, you can try to generate an integer sequence from this object, look it up in the database, and very often it or something very similar has already shown up in the database, and you can make connections that would otherwise not have been discovered. Okay, so that's one classical use of machines, okay, or data tables. The other major use is what we call scientific computation, or more colloquially, number crunching. And so this is sort of this is what you would think of when you say you use computers to do mathematics. You're just doing some massive simulation, or just solving a whole massive amount of equations. So you want to model a dynamical system, or find roots of a polynomial, and so forth. This is scientific computation. And so it's been around for over 100 years. It predates electronic computers. Arguably the first major scientific computation was done by Hendrik Lorentz in the 1920s, using a team of human computers to model a fluid flow for a dam that was being constructed in the Netherlands. It had to invent floating point arithmetic, actually, to run the simulation. Okay, and the dam was successfully built, and the predictions held up. Okay, so those are the traditional. And these sort of number crunching things, so of course they do lots of arithmetic, lots of floating point operations and so forth. But they can also do certain sort of logical tasks. So like if you have a whole bunch of statements and some are true and false, they're either true or false, and some relationship between them, you can try to work out, kind of like solving a Sudoku or logic puzzle, which ones are true, which ones are false. There's a class of problems called satisfiability problems, SAT solvers, for which we have automated tools to solve these things. So certain math problems can be kind of reduced to sort of this game, where there's just a certain number or a logic puzzle, where there's a certain number of statements that are true or false, and a certain number of hypotheses, and can you get conclusion hypotheses. And some of that you can automate, as long as it's not too large. Now, a lot of mathematics you can't solved by this method, because it only works if you have a finite number of hypotheses and a finite number of conclusions, but sometimes it works. Let me just give you one example of a massive satisfiability problem. Okay, so there was this long-standing conjecture called the Boolean Pythagorean triples problem, which was only solved by a massive computer search. The question is that so these Pythagorean triples, like 3, 4, and 5, which are the sides of a right-angled triangle, but they're pretty sparse. There's not that many of them. It's 5, 3, 4, 5, and then there's 5, 12, 13, and so forth. They're fairly rare. But it was believed, and it's now proven, that if you take the natural numbers and you divide them into 2 pieces, these patterns are common enough that one of these, no matter how you divide the natural numbers into 2 classes, one of them is guaranteed to contain one of these triples. And in fact, you don't even need to partition all the natural numbers. You just need to partition 7,825 of them. Okay, so I can't. This pointer does not. Okay, there's, no matter how you decompose, you break up this set into 2 pieces, one of them contains a Pythagorean triple. On the other hand, if you do it with only 7,824, there was a way to do it for which neither class contains a triple. So that part is fairly easy. You just need to exhibit one partition that doesn't do that, and you can check that with a very simple computer program. But the hard part is the second part, because the number of ways in which you can break up this set into 2 pieces is 2 raised to the 7,825, which is a humongous number. You cannot check all of these by hand. So this is basically like a logic puzzle or Sudoku with 7, 8, 2, 5 boxes. But you can show that there's no solution to the Sudoku. At the time, it achieved the record for the world's longest proof. The proof generated a certificate which required 4 CPU years I need a megahertz. Okay, that's not a valid unit, but okay, 4 years of a certain CPU. But okay, but okay, but yeah, the proof was originally 200 terabytes, which okay, maybe the astrophysicists have bigger sets, but to us that was a large number. Okay, they managed to compress it down to a mere 68 gigabytes, but at one point it was the world's longest proof. Okay, so this is sort of an example of traditional ways of using computers in mathematics. Okay, but what is exciting is that there are several new ways of using computers, which individually people are finding niche ways to incorporate them into doing. Into their workflow. Okay, so of course there's mundane ways. Okay, so we all use email, we all use computers to write our papers and search for paper and download things from the internet and so forth. But I'm not interested in these mundane things. But the 3 new ways that are beginning to become transformative, but not yet at the killer app stage. So one is machine learning. So using things like neural networks to find patterns and relationships that from large data sets that you just could not see from humans, or possibly you could discern them from a more traditional statistical analysis. But the thing is, most mathematicians don't have this training to work with these data sets, and these machine learning algorithms could like automate this at a scale that we just cannot. We don't have the training to do. Then, of course, there's the high-profile large language models, ChatGPT, Claude, and Gemini, and so forth, where they are well. First of all, they're making other tools easier to use. So it becomes easier to run machine learning or to code up one of these things if you start asking large language model to do it for you. But they are beginning to solve some simple problems in mathematics or to assist with sort of secondary tasks in a mathematical activity. So far, they are not good at directly solving hard math problems, but that may not be the best way to deploy them. Then these formal proof assistants, which are very complementary tool, these are like very, very fussy proof checkers. If you write a proof in a very specific language, these proof assistants will go through every line, and it will either say tick, this is a correct proof, or compilation error, this is a correct proof up to line 567, and now there's a syntax error. Much like you would compile computer code, except that computer code generates executable programs, and formal proof assistants, they are also computer languages. They can technically also do that, but they can also generate proof certificates. And that is, well, I mean, that's nice by itself, but it's also enabling other things, like, for example, allowing finally mathematicians to collaborate in large groups, which we've basically not been able to do before, except with like a lot of painful effort. Individually, these are becoming useful, but actually what's really promising is that by combining them together, I mean, that's where the killer app's going to come up, some sort of synthesis of all these. Right now, these tools don't talk to each other very well, but they should in the future. Okay, so let's talk about, I think I'll talk about proof assistants first. So computer-assisted proofs have been around for about since the 70s. The most famous early example of a computer-assisted proof was the four-color theorem, which required checking a lot of cases. So I didn't talk about, the slide don't show the proof, but it involves generating a list of about 5,000 special graphs and verifying these graphs have various properties. And at the time, some of these properties could be verified by computer, and by computer, I mean a 1970s punch card type computer. Some of them could be proven in a very mechanical way, but not proven by a full computer. In fact, I think Edmund Harkin wrote down for each of these 5,000 graphs a few lines of no, actually they got Harkin's daughter actually to write down like a 5 or 6 line justification of a certain property for each graph, and like they had to do it 5,000 times. It was very error prone. They had to revise it several times because it was a long time. It took like 20 years before a computer-assisted proof which was acceptable by modern standards was produced. So the proof, there was a new proof which was a bit simpler. It uses only like 500 graphs, but more importantly, the computational part of the proof was a statement that you could state what you wanted to be true, and then anybody could spend an hour or two writing a computer program to verify this specific computational task, and this is something that you can run in seconds on one computer and verify it, and they supplied the code. But you still have to trust the code. You know, maybe the person who coded it had a bug. If you really want a formal proof certificate that there's a rigorous guarantee that the statement can be proven all the way from the axioms of mathematics, that was only done in 2005. Where they used the proof-assistant clock to give a complete proof. So you see, it takes decades traditionally to get to the point where you can actually formalize a theorem. Another famous example is the Kepler conjecture. So this is a conjecture from the 17th century that if you want to pack oranges or cannonballs or whatever in space, there's this sort of obvious way to do it, which is the way that you see oranges stacked in supermarkets. It's called the cubic central hexagonal close packing, and that has so there's some empty space between these spheres, and the proportion of space which is occupied by the spheres is about 74%. This number here, pi over 3 root 2, and it was conjectured by Kepler that this is the best way to do it. That there's no other better way to pack these spheres than the sort of the obvious algorithm. But this turned out to be remarkably difficult to prove. 2 dimensions is not too hard, but the 3-dimensional version is really, really hard. There was a strategy. So already by the 1950s, there was a strategy. So whenever you have a packing, it creates a way to decompose space. Okay, so every sphere here comes with what's called a Voronoi cell. So all the points that are closer to this sphere than they are to any other sphere, there's a certain polytope, there's a certain polyhedron around that sphere, and so you can every time you have a packing, you get all these polyhedra, and they have various faces, they have various areas and volumes, and there's various relationships between. You can relate, like if you can relate the volume of these touching polytopes with the volume of these. There's various inequalities that you can do, and they're also related to the density of the whole system. So in theory, if you could collect enough inequalities between all these different polyhedra, and then you run some sort of linear program, you might be able to just deduce the bound on the density. And so this was a promising strategy. In principle, you only need a finite number of these things. So this is something that a computer could potentially do, as opposed to the whole packing problem where there's an infinite number of these boards. So people tried this. There were many false attempts, false proofs proposed. So this was finally done in the 90s by Hales and Ferguson. So the thing is, the strategy as stated doesn't quite work. You have to replace these polyhedra by more complicated polyhedra which don't have an obvious description. He kept tweaking the definition of these Voronoi cells, and also things like instead of taking volume and area and sort of obvious measures, he had introduced a score, a numerical score for each polyhedron, and the score kept changing as the proof advanced because they tried one thing and it didn't work, and they added one more bell and whistle and it didn't work. And finally, they got it, but it was a very controversial proof. So I'll just quote. So Hales wrote that every time we encountered difficulties in solving this problem, we could adjust the scoring function to skirt the difficulty. This function became more complicated, but with each change, we could cut months or years of my work. This incessant fiddling was unpopular with my colleagues. Every time I presented my work in a conference, I was minimizing a different function. Even worse, the function was mildly incompatible with earlier papers, and this required going back and patching the earlier papers. So they finally did it, and yeah, so they chose a very carefully constructed score function, and there's 150 variables, and they did a linear program, and they verified it. They didn't start off with computer assisted. They were hoping to do pen and paper proof, but it was they were forced into a computer assisted proof. Yeah, so at the time, quite a large proof, 250 pages. And 3 gigabytes of various notes and data. They sent it to the top journal of mathematics, the Annals of Mathematics. It took 4 years to referee, which actually, Annals has taken longer for some papers, but that was pretty long. But the referees could not, they said they were only 99% certain of the corrections. They could not reproduce the calculations. And so it was I know it's the very unusual thing of putting a caveat, like a disclaimer at the beginning of the paper that the editors do not vouch for the correctness of this paper. They have since removed that from the current online version. Yeah, so it was very controversial at the time. There was a lot of incentive, particularly from Tom Hales, to actually formalize this in a computer language for which there was just no doubt that there was no just a little sign error somewhere that invalidated the whole thing. So he made a project. He got a fly spec. He estimated it would take 20 years to formalize every single step, and he was very pleased that it only took 11. And yeah, so it was the form proof was finally published in 2017, and with many collaborators. So that's sort of the where things stood until very recently. Like you could formalize, but it was so painful that only for very high profile project would you want to do it. But now the technology has gotten a lot better. Still not perfect by any means, but we are beginning to you don't have to spend years to do these things. So you can do these. You can formalize in weeks. So like very recently, I put together with 4 co-authors, we proved a conjecture in combinatorics. It's called the polynomial Riemann-Roentgen conjecture, although despite the name, is actually this particular conjecture like introduced by a computer scientist, Catalin Martin. It's not important what the conjecture is. It's just it's some piece of math. We proved it by traditional means. We talked to each other. We exchanged emails. We worked on Blackboard and so forth. And we had this 33-page paper, which actually just got accepted in the Annals, proving this result. But then we decided, I decided that this was a good project to try to test the most recent infrastructure for formalizing these things in a more modern proof-assistant language called Lean. So we opened a project, and it took about 3 weeks, and involving 20 people, most of whom I had not met previously. The thing is that, as I said, this group of 4 people, that's about 4 or 5 is close to the maximum size of a math collaboration currently. Because in math, if you have to trust every single piece of an argument. So if someone supplies a proof of one step and you don't understand it, maybe there's an error in it, then the whole thing can be wrong. And so you have to verify every contribution that everyone else contributes. And this is a significant limiting factor in enlarging the size of collaboration beyond 4 or 5 people. But you can crowdsource a proof formalization in ways that you cannot in a traditional formalization. So the way a modern proof formalization, wow, I just realized my time is almost, okay. I'm going to have to speed up quite a bit. Okay, yeah. But the way a modern proof formalization works is that you take a big, complicated statement and you break it up into lots of little pieces, lots of little lemmas, each of which is fairly simple, maybe a simple consequence of other pieces. And so, there's this statement on the bottom. So the statement that we have is called the PFR conjecture. That represents this little bubble at the bottom. At the time of when I took the screenshot, this was an empty bubble, which means that it hadn't been proven yet. But there were other bubbles that we stated all these other facts that this statement depends on these 4. Some of these we'd already proven. Some are ready to be proven. There's a color coding, which I won't talk about. But the thing is that you could then crowdsource, and people could volunteer. I'm going to work on one proposition, and you just need to prove this one thing that this lemma follows from the 3 things above it, and you don't need to understand the whole proof. So this was a theorem in combinatorics, but most of the contributors were not combinatorialists. And in fact, many were not even professional mathematicians. They were computer scientists, people who were from industry, people who just liked solving puzzles, actually. So we got a very broad class of people to work on this, and like every contribution had to be formalized, had to be certified by this language Lean, and so like we could trust all the it didn't matter that I didn't know these people, and maybe they make mistakes, but if they make mistakes, it wouldn't get accepted into the project. And so we've been able to do these large-scale collaborations. Okay, so I think I will skip. Yeah, this is just one example of what lean code looks like. It looks vaguely like math, but also like computer code. It's some sort of weird hybrid of both. Okay, but I think I will skip the. Yeah, so in many ways, it's more tedious. It's still more tedious than writing things traditionally. I would say that currently, if you want to write a formal proof, it's roughly about 10 times longer than writing a proof in the traditional way, using our LaTeX language and so forth. And so, like, it's not worth doing. At the current stage, like for everybody, you have to still pick and choose which projects you want to formalize. So we're still kind of focusing on relatively high-profile projects. Okay, so maybe the highest profile currently is that Kevin Buzzard is 1 year into a 5-year project to formalize the entire proof of Fermat's last theorem. And he estimates in 5 years he might not formalize all of it. But so Wows's proof was in the mid-90s. He wants to reduce at least that statement to facts that were already known in 1980. And then there's still some work to formalize those, but that seems to be the current goal. Okay, maybe I'll tell you. So that's one way in which mathematics is being transformed. That we are now able to collaborate at large scales. I gave you a project example where you're formalizing something that had already been proven. Later, hopefully, I'll talk a little bit about formalizing mathematics. I mean, where the results haven't been proven yet, and the formal structure is actually part of how we actually arrive at the proof. Okay, so another direction is to use these large language models. So this is one of my favorite stories. So maybe so this is a story from knot theory. So knot theory is one of the branches, or is a sub-branch of topology. So you make a loop in space. There are various knots you can make, and some knots are different from each other. Like some you can deform from one to the other, and some are genuinely different. And so one of the basic questions in knot theory is how can you tell whether two knots are equivalent or not? One of the ways we do it is that we assign these things called invariants. Okay, so there's certain numbers that you can assign to a knot, such that if you continuously deform the knot around, these numbers don't change. And so if two knots have this different invariants, then they are not the same knot. Now, there's various different ways you can construct invariants. There's something called the signature of a knot, which is a certain integer. And it comes from combinatorics. You count crossings and whether you cross over and cross under, and there's a linking matrix. There's some combinatorial recipe to generate knots. And then there are these geometric invariants, where you look at the space outside the knot. So this is three-dimensional space with a knot removed. This is what's called a hyperbolic. It's usually an example of what's called a hyperbolic space, and you can define things called hyperbolic volume and hyperbolic cusp volume, and there are lots of real and complex numbers attached to these knots. Okay, so I'm not going to define these things, but this is a partial database of a whole bunch of knots, and various statistics attached to them. So there are these two unrelated ways to generate invariants. There's a combinatorial recipe, and then there's these geometric recipes, and there was no connection known between these two. A bunch of, I forget the authors, it's not listed here, but a bunch of mathematicians decided to just throw machine learning at this. Okay, could you get a neural network, like if you just feed the neural network the geometric invariants, so these like 20 real complex numbers attached to these knots, could you predict the signature? And they found that there's a network that they could make a neural network could do this with like 90% accuracy or 99% accuracy, something really superbly accurate. So this told you that there must be some relationship. These invariants were related, but the relationship was given by this black box, this neural network that there's this very complicated set of weights and functions. And so you had to somehow open up this black box and understand it. So they did a very basic analysis on this. So once you have this black box, it's basically a box that takes in 20 numbers and spits out one predicted number. And so you can just turn these knobs, like you can change one of these numbers and see how much it changes the output. And they found that of these 20 inputs, 17 of them did almost nothing. But 3 of them were really important. There were 3 of the 20 inputs that really made a big difference. And there were three inputs. It's called the longitudinal translation and the real and complex parts of the meridianal translation. These were inputs that they did not expect to be important. For example, they expected the volume of this half-wave volume to be the most important invariant, and it was actually almost insignificant. So with some analysis, they realized that there were three inputs that were really key, and then they could plot. They could plot those inputs against the signature and so forth, and then visually they could see a relationship, and then they made a conjecture based on sort of visually fitting a curve to the data that they saw. Once they had this prediction, they compared it against the neural network, and the neural network said, no, this conjecture can't be true because here are some examples of knots where that don't do this. But the way that the conjecture failed led them to see how to fix the conjecture. They add an extra term to make it more accurate. And then once they had the right form of the conjecture, they could then actually prove it theoretically. So it was really this conversation between theory and experiment and conjecture and the machine learning and the humans. And so they did rigorously prove a connection between these facts. So this is another way in which mathematics is changing, but it needs data. Okay, so what made this work was that there was already a database of 1 million knots. They added 2 million more to an existing database, and then they were able to do this. Right now, we still have most of fields of mathematics do not have enough databases. We are still a data poor science in many ways. Okay, I have some slides on large language models, but maybe there's not much that hasn't already been said. This was sort of, I mean, large language, sometimes they can solve really, so for example, now they can solve like Olympiad level problems, high school math competitions that most high school students can't solve, and sometimes they can get perfect answers, and sometimes they can't do basic arithmetic. So you can give it an arithmetic sum, and it will just happily spit out the wrong answer, and then you point out that it's wrong, and say, "Oh, I'm sorry, I had a typo," and so forth. It's pattern matching. It's weird that somehow the set of tasks that large language models are good at is almost orthogonal to the set of tasks that humans are good at. So things that we find hard, they can find easy, and things that we find easy, they can find hard. It's a very weird tool, So by themselves, I mean, they're already useful by themselves for various things. Like if you want to quickly learn a subject that's not quite in your field, it's like a really good version, interactive version of Wikipedia. So you can do some sort of literature search for basic things. You can suddenly write code. You can format. You can write. If you have a tricky LaTeX image you want to make, you can do that. So there's lots of secondary tasks which is very useful. You can also ask it for suggestions of how to solve a problem, and it'll give you 10 suggestions, of which 7 are rubbish, and 2 are kind of things you already thought of, but 1 might be an interesting idea. People are beginning to combine all these different ways of using computers together. So this is a very promising approach by various groups to construct. So one of the biggest problems in fluid equations, in mathematical fluid equations, is to construct solutions, initial conditions to fluids that actually develop singularities in finite time. There's a particular equation called Navier-Stokes that we really want to construct solutions to, but actually there's a lot of other fluid equations that are simpler that we would love to rigorously show blow up. So there seems to be this two-step process. So the way to do this, we think now, is to first use machine learning and similar tools to first construct approximate solutions that almost blow up, but to really high accuracy. They're within like 10 decimal points of precision to something that actually does blow up in some sense. And then combine that with some really rigorously verified perturbation analysis that shows that any approximate blow-up solution has to be close to an exact solution. So you can use whatever non-rigorous, error-prone AI you wish to find the candidate, but then you couple it with some rigorous verification at the end. And this has worked already for simple fluid equations, and we're so slowly climbing the ladder of more and more sophisticated fluid equations. So I think in 10 years we might actually get the Navier-Stokes. It'll be a big program, but we're very close here. Okay, so as you saw, large language models are very bad at arithmetic, and they make so many mistakes. So like using them to directly calculate in math is very unreliable. Weirdly, it works better if it's a very high-level math with not much numerical calculation. But the more numerics there are, the more error-prone it is. So what we're slowly beginning to realize is that the way to proceed actually is to get the large language model not to directly do the math, but to generate code in a more reliable language, like Python or a traditional computing language, and then run that to solve your problem. And this seems to be a much more promising paradigm. For example, there are many problems where the task is to construct some high-dimensional counterexample, and there's some really high-dimensional space of possible candidates, and doing standard optimization or machine learning doesn't work, but instead writing a much smaller computer program to generate a candidate, which is high-dimensional, running that, and doing some iteration on that code, it has already begun to improve some mathematical problems. Yeah, for example, the fastest matrix multiplication algorithm for large matrices now is due to this this AI fund search, which was created by Google DeepMind. And there are these ongoing artificial intelligence Math Olympiad challenges. I'm actually on the scientific advisory board of this one. So we are the dream is to get an AI to actually achieve gold medal performance at one of these Olympiads, hopefully using something which is open source and something that can actually be replicated by other people, and not just requiring some $10 million of compute and lots of fine tuning. But we now there are open source models now that can so we haven't yet achieved performance at really the limited level. One of the problems actually is grading the output of these models. We don't have enough human graders to evaluate the output here, so we have to content ourselves working with problems that have numerical solutions, like a problem whose answer is a 3-digit number, because that we can check automatically. But they did surprisingly well. So on a medium tier Olympiad level, they can now achieve 50-60% performance. Again, the secret was to not solve the problem directly, but to generate code that would then solve the problem. Yeah, okay, so there's a similar, there's another algorithm that solves geometry questions, but maybe I will skip that. Yeah, so there's been success, so instead of outputting in Python, people are beginning to figure out how to get AIs to output in these proof verification languages like Lean. So you can, so there's this recent success in solving genuinely Olympiad level questions by converting the question into a Lean statement and then using a version of AlphaZero's program, which is what DeepMind used to solve Go, for instance. And viewing these math problems as this massive Go-like game where there's certain moves you can do, and you just need to get from A to B. And then they can prove quite difficult these Olympiad level problems after massive amounts of compute. Although the proofs are really weird. I mean, the proofs are completely inefficient. Okay, so for example, they solved this IMO problem, and the first step is to induct on the number 10, which makes no sense. It's actually it's a step that you could just delete, and it would still actually be a valid proof. Yeah, and then actually there's some human-edited commentary. They spend 16 lines proving a lemma, and then it gets discarded without being used. It's a completely alien type of proof. This is not what a human would write. But it can solve these questions, and we don't really understand why. Partly because we don't have access to the actual source code or anything. This is all just what DeepMind reports. But anyway. Yeah, but you can solve these massive problems. One thing I've been involved in is trying to use these tools to actually prove new math rather than just solve existing questions. So I had created this test project where, so one thing which these tools can maybe do is do mass exploration of many math problems at once. So mathematicians right now, we can only work on one problem at a time, spend months on it, and then we go to the next problem. But potentially now you can try to attack millions of problems, not the most difficult problems, but millions of sort of medium difficulty problems using computers. And that is a different style of more experimental mathematics, which I think will become more and more prevalent. So here's one example, just as proof of concept that we started doing. You may be familiar with various laws of algebra, like the commutative law, x times y is equal to y times x, and the associative law x times y times z is equal to x times y times z. And so some operations obey these laws and some don't. And so we just procedurally generated 4,000 laws of algebra. Okay, so like the commutative law is this one here, x times y equals y times x, but maybe x equals x times y, and so forth. So we just generated all these equations, and we give them names. And some of them imply other ones. For instance, if x is equal to x times y, then it turns out that x times y times z is always equal to x times w times u. There's some algebraic deduction that you can use some of these laws to prove other ones, but some laws are not connected. Let's see, for example, this law x equals x times y does not imply x times y equals y times x, because you can construct operations that obey this one but not the other one. And so we have these 4,000 or so laws, and there's like 20 million pairs between these laws. And the question is, which laws imply which other ones? And so the project is basically just to explore this entire graph. So any given edge is fairly easy. Someone who has a graduate level exposure to algebra or something could maybe just take one of these pairs and by hand, in half an hour, to figure out which one's true, which one's false. But you have 22 million of these things. You have to do it in an automated way. And so we managed to do this. Okay, so in about 2 or 3 months, we completely determined this graph. Some were easy, some were hard, but we didn't know in advance which ones were easy, which ones were hard. And so this was crowdsourced. There's going to be a paper with about 50 co-authors, which may be close to a record, actually, in mathematics, so we have these 20 million tasks, and so people can work on 1 or 10 or a million of these. They can deploy their favorite AI tool and so scan all of these implications and see which ones they can do and which ones can't. And then it all gets uploaded to a central database, and everything has to be verified in Lean. So you can't corrupt. I mean, if there was one of them that was wrong, it sort of ruins the whole thing. But everything has to be certified. And most of our collaboration, we didn't know each other. There were people who, most of them are not even mathematicians, but different people contribute different things. Some people might one person might figure out one relationship between by hand between two of these equations, and then someone else would generalize it and then write a computer tool in, say, Rust or something to search all the other implications, and then a third person would take that computer program and make it produce output in Lean that would then get uploaded. And like no single person could do all this. We always have also these beautiful visualizations that I have no idea how to write. But it all got put together. We used, actually, surprisingly, we didn't actually use modern AI very much. So we didn't use all these fancy tools, partly because we didn't have the budget for the computer or anything. We used much more classical AI, things called automated theorem provers that I mentioned very briefly at the beginning. The main application currently of these large language models was to build the graphic interfaces around the project. But they were not super successful at the actual tasks themselves, but I think that's just a matter of time. But it's a new type of doing mathematics which you couldn't do without all these tools before. I mean, you could not prove 22 million of these implications with just with humans. Where do I see all these tools in the near future? I mean, the naive thing is that you could just ask put your favorite problem into ChatGPT and it will give you the answer. This does not work. But there's lots of side tasks which are very, very useful. So semantic search, it's already beginning to get good at, you write a very vague question, I need a tool that controls this random variable given this assumption, but I don't know what to search for. And if it's something fairly standard, it will give you exactly what it is. A tool will tell you exactly what it is. Or it can give you, it may not give you the same right answer, but it will give you some keywords that you can search for. Formalization is still a pain. As I said, it takes 10 times longer to formalize a proof than to write it by hand. But AI tools are beginning to chip this down from 10 to 9 to 8. There are lots of little AI assistants that can speed up either the task of breaking up a big proof into lots of little pieces or filling in each of the little pieces. I think once we have more databases, we can do a lot more with math than we can currently. So a big bottleneck is just we have to actually get people to create high-quality math databases, and we don't have enough. I think we need to change or at least broaden our workflows of the ways we do mathematics. So the traditional project is you pick one hard problem or maybe 2 or 3 related problems and you work towards that goal, and every step has to be correct. You have to have 100% validity with your steps, otherwise you don't have a proof at the end. But many of these tools, particularly machine learning and AI tools, have failure rates. Sometimes they give you rubbish. So either you need to filter everything through a verifier like Lean, so that's one possibility. But more generally, you need to somehow have a very modular project where it's okay to have a failure rate. Like instead of solving one problem, you solve 22 million problems, and if an AI tool only solves 10% of those, that's already 2 million problems done. And you add that to the pile, and then you run another AI. So we don't do that currently. But I mean, in the other sciences and in the real world, you deal with failure rates. But so we need somehow to embrace ways to do mathematics, how to use fallible tools to still produce rigorous results at the end. But it seems like it is possible. And then the final thing I think which will potentially be transformative is that we can use these tools to find new ways to teach mathematics. So I mean, already AIs are kind of being used. Okay, so clearly they're being used to do homework assignments, right? But as TAs, if it's done in a properly curated way, where the AI teaching system does not give you the whole answer, but maybe it would do all the calculations for you, but you still have to supply the high level direction for it. Or conversely, it will give you the high level prompts, and you have to do the step-by-step details. It could really enhance pedagogy. I think textbooks can be much more interactive. I mean, you read a math textbook, if there's a step you don't understand, you have to ask the instructor how to explain it, or you need to spend hours working out by yourself what was really meant, especially if there's a typo. Future textbooks should come with AI assistance. You can just ask, can you explain Lemma 3.5 how does you can ask really specialized questions. You can open up the proofs and maybe you can get passed to a lean version of this proof, or you can every sentence that is you can expand out into a much longer explanation, expand and contract as needed. There's already some prototype software for doing this semi-automatically. So that's also, I think, very exciting. So I think those are all the different things that I see. So thank you very much.
All right, thanks very much for the talk. So he's going to take some questions. And there's a button close to your seat that you can use to ask questions. If that doesn't work, I can come over to give you the mic. All right, so questions? Yeah, please go ahead.
First of all, Professor Tao, thank you for the very wonderful and engaging, exciting talk. Yes. Okay. Hello. Thank you, Professor Tao, for the very wonderful, engaging, and thought-provoking talk. My question was in regards to your mention of some areas of math lacking the data necessary for machine learning algorithms to tackle them. Mm-hmm. It seems like a lot of the problems you presented were very combinatorial in nature and very amenable and approachable mm-hmm. by computers or machine learning algorithms to solve. Mm-hmm. So I was curious as to whether it'd be possible to use computers or machine learning algorithms to attack problems in other areas of math that might not have as much data, or I guess have as much.
Right.
Yeah.
Yeah, that is a challenge. I mean, on the formal side, actually, algebraic types of mathematics actually been easier to formalize than sort of analysis combinatorics. But for using and weirdly, as I said, large language models actually seem to be able to do high-level algebraic reasoning a bit better than high-level combinatorial or analytic reasoning. Somehow in algebra in particular, there's often sort of a canonical way to do things, or canonical way to define a certain object and how to use it. I'm not an algebraist. So I mean, Yeah, most of the data sets that I can't even imagine what data set we'd need. Okay, so some of it is just collecting literature all in one place, which is already sort of useful. There's so many fields where the known results on this area are just completely dispersed. And actually, hopefully, AI can help sort of doing literature review. That's another possible use case. Another thing is that like mostly we only the data that's out there is mostly only the results, the proofs that actually worked. So actually, it's like one thing that these DeepMind type explorations have found is that actually it's very important to have in the training data not just complete successful proofs of various problems, but also failed proofs that got halfway and then stopped. And then maybe in their database they also have another proof which of something else, but they also got that to something like that halfway point, but they were able to keep going. And then somehow they're able to combine these two things. So one that proved the right thing, but stopped halfway, and then one that proved something different, but kept going, and they could combine them. So, behind every successful proof, there's like months and months of trying things that didn't work, and then figuring out why they didn't work, and then changing your proof strategy. And this is something that is almost completely private. We don't share this information. Maybe if you're lucky, your advisor might share one of these stories or something. Or you are in a collaboration and you see in real time one of your co-authors do this. But it's not something that we share. It's the same reason why we don't publish negative results much in the sciences. And maybe we need to do more of that, just to show the process. But I mean, the AI in particular has sort of no access to this data. And so they can either produce something that looks like a correct proof or something which is rubbish, but they don't know how to fix it when things go wrong. They're very bad at that right now.
In one of the example, you mentioned there were lots of propositions. Most of them were easy to formalize, but a few were very hard to formalize, right?
Yeah.
Is there any common structural pattern for those hard to formalize propositions?
That's a good question. Yeah, what we found was that there's these sort of techniques. So there's these 20 million implications, and we had certain techniques. So you could try using an automated theorem prover. You can play with small examples, like just play with small multiplication tables. There's certain constructions based on linear algebra, and each one sort of covered some percentage of these. And so there's this sort of residual set of survivors that just sort of were somehow immune to all the previous techniques. And they were a very eclectic set. We don't. The only thing in common is that none of the easy methods worked on them. So they did kind of look like. So there's sort of this math from Mars aspect. So as I said, there are some famous laws of algebra, like the associative law and commutative law, that are very, very well studied. And actually, all the implications involving those were very easily dealt with. And then there's just these few random survivors. It's like they're just passing through several filterings of different methods, and there wasn't a common pattern to them.
Maybe you can collect all of them and train a model just for the hard propositions.
Yeah, we were hoping. I mean, in some sense, it was a pity that the project succeeded in like 2 or 3 months. I was hoping that we'd get stuck with some core of like 1,000 hard ones, and there'd be different people trying increasingly clever things. But we ended up with like a core of about 100 problems that would, and so and some of them implied other ones. So like if you solved one, you could get 10 for free. And so like the last 100 were just done by hand. We didn't use fancy AI or anything at the end.
Thank you.
A very interesting lecture. I'm curious if you've investigated like the latent representation of proofs or parts of proofs, because one of the breakthroughs that happened with language models was to have a representation of first words and then combination of words and then ideas in a high-dimensional space. And with that, the models are able to recognize patterns and form things. And I'm thinking there might be an analogy of this in proofs and also objects of things like knots and so on.
It's certainly possible. We have found, for example, there are databases of graphs. And there's different ways you can describe a graph. You can describe edges, you can describe the adjacency matrix, which is a big string of ones and zeros, or you can list the edges. And there's some other ways to construct graphs. And we have definitely found that the representation matters. That some machine learning algorithms, when trained on graphs with the wrong representation, are much less efficient. And we don't really understand what is, like right now, basically, there's this trial and error process every time you say, I'm going to use a neural network to attack my problem. You have to make all these decisions at the beginning, how you represent your data, what your parameters are, and what you count, what is your loss function. And it's an art. It's not a science yet. It's possible that the same thing was true for proofs. Yeah, I think for now, these proofs are just being tokenized as text, and somehow large language models they just have sort of a general understanding of text as written by humans. That this seems good enough.
Yeah, but if you got away from the text and got closer to the intrinsic mathematical operations and logic and reasoning that's parts of the proofs, and that it could build predictions and form patterns. And
yeah, theoretically. I think that the thing is, it's very hard to compute large language models because they have trained at great expense on massive amounts of text, and there's no comparable database for these sort of diagrammatic representations of proofs. That
maybe you could start with all the lean proofs and train from scratch a small
0.001% of the size of sort of the internet, which is sort of what LLMs get to train on. Yeah. But this will happen. I think. Yeah.
Thank you.
Last question.
So thank you. Thank you very much for your talk. So the examples you gave were from specific areas of mathematics, knot theory, number theory, group theory, where already the problem was pretty well identified.
Yes.
And then they had some proof strategy which they explored further.
Yes.
Now, in the 1950s and 1960s, as you know, what people discovered is that people in different areas of mathematics were doing similar things in different languages, and this led to the development of category theory and the notion of functor and so on, in order to transfer basically structures and results from one area to another. And this discussion of latent structures reminds me of that. Is there any attempt to use the language and formalism of category theory to, for example, build high-level proof assistants which do not depend on a specific set of objects, like a specific universe of objects?
There are proposals. Okay, yeah. So there's this thing called homotopy type theory, which is, in principle, well designed to do that. It writes proofs in a way that you can really deform continuously the objects that you're working with, and the proof somehow survives. None of the major proof assistant languages currently are based on that framework. In principle, it could be done. Part of it is that most of mathematics is not written in these frameworks yet. It's written in much more orthodox, set theory type things. And so, in order to actually have enough of a critical mass of people working on these things, you need to work in a language that most mathematicians are familiar with. So it's sort of two steps too. Like ideally we could write proofs in this sort of abstract language, but that's not what we do as a working mathematicians every day. So the amount of effort that people would put into formalizing that would be very, very small right now. Maybe once formalization becomes a lot easier with AI assistants, we could start doing it that way, and maybe that would actually be a much more efficient way. You could easily take a proof in topology and change it to a proof in geometry or something, without having to redo everything.